Now we want to start doing some mathematics with this. And in this case, the question is asking us, calculate the amount of energy needed to vaporize 346 grams. There is no change in temperature here because there's no change in temperature during a phase change. Now, when we have a double unit or a slashed unit like this, remember that we can write that as a conversion factor. You can either plug into a formula or do it the way I'm doing as a conversion factor. So that's telling me that for every 1 mole, it's going to take 40.79 kilojoules. Well, I don't have 1 mole, so we have to find out how much we have. So the first step is to go mass to moles. Mass to moles use molar mass. So we're going to have 2 steps. Mass to moles use molar mass, and then we'll get to the energy portion. So I have 346 grams of water. I want to get rid of grams and go to moles. 1 mole is 18.02 grams. Now I'm going to use this as a conversion factor. I need to get rid of moles, and I want kilojoules. And my new conversion factor, my delta H of vaporization, tells me that for every 1 mole, it's going to require 40.79 kilojoules of energy. Now, if we do that mathematics, we're going to get 783 total kilojoules. Now let's talk about this just a moment before we forge ahead. Do you notice the example said how much energy is needed? What we are doing in this process is we're taking water as a liquid and going to water as a gas. Now if you wanted this to happen, would you put it on the stove or would you put it in the freezer? Well, you'd have to put it in the stove if you wanted to force it to happen. And so that means we're adding 40.79 kilojoules as a reactant. That also means that our energy is positive. Our enthalpy is a positive value. This is an endothermic reaction. If we were to sketch out a little energy diagram, that would mean that my reactants are at lower energy than my products. This isn't a heating curve, cooling curve. That's an energy diagram. So it would mean adding heat to go from reactants to products. Now, if we were on a temperature or cooling curve, if that was temperature versus heat, we'd be at a flat zero slope segment of our graph. This is what we did, is this segment here, this is occurring, vaporization occurs at the boiling point. It's an endothermic process. Slow this down, rewind this, do whatever you need so that you can capture that understanding, and we'll apply it in more detail in class. Let's go on to number 2. Number 2 says calculate the amount of energy that is released. We have a release of energy in this case. So right off the bat, you should know or be able to tell me that this is an exothermic process. Now, I recommend when you're doing these to do a quick sketch of your heating curve, cooling curve, and figure out where you are. So you can heat a solid, melt a solid, heat a liquid, vaporize, heat a gas. Now for water, you should know the boiling point of water is 100 degrees Celsius and that the freezing point is 0 degrees Celsius. So if I look at what I'm given, I'm going from 98.6, so I'm a little bit below the boiling point, down to 32.3. So all I have is one step. And that one step involves a temperature change. So I'm going to use the MCAT formula. Q is mass times the specific heat capacity of water times the change in temperature. Now, notice that's my initial temperature. That's my final temperature. That will be important as we work this. So Q, which is equal to delta H at a constant pressure, mass has to be in grams because my heat capacity is in grams. So I'm going to convert my kilograms to grams. I'm going to multiply it by the specific heat capacity. Now, when you do a delta T, it's always final minus initial. And what's nice about that is if you set that up properly, you will get the sign that you need for exo or endothermic reactions. Now, if you solve that mathematics, you may want to pause the video and try that yourself. You're going to get a negative 2.9 times 10 to the 5th joules. It's negative because when energy is released, it is exothermic. You're cooling the liquid. If you want to cool your iced tea very quickly, or you've got a can of pop that's warm, you're going to toss that can into the freezer to get it to cool down. Remember, if the freezer is the better choice, that's a good indication that the process that you're looking at is an exothermic process. Now, I'm going to stop this video at this point, and what I would like you to do is work on your own. This would be the best way to learn, is for you to try 3 through 7 on your own. Give them a shot, and once you've tried them, then look at the next video and you'll see me work them out so we can reinforce the learning that way. If you don't try them on your own, you'll see me explain them, and that has some value, but it doesn't have as much value as you're trying first. So you always want to try first and then let me give you that boost in learning if you get stuck. So see you in the next video clip.